You're in session B2, first one of the morning here. It's titled Pedestrian Bridges, Unique Design and Analysis. My name's Jeff Sweat. I'll be your moderator. I work for the Washington State DOT in the Bridge and Structures Office. We've got a couple interesting presentations today. Our first one is titled the Fanny Appleton Bridge. It's part of the Longfellow Bridge Design Build Project in Boston. We've got two speakers. Our first speaker is William Goulet. He's a structural engineer at STV Engineering Incorporated. He's got 10 years experience. He earned his bachelor's at the University of Massachusetts. He's got his master's degree from Norwich University. He's worked on several unique projects and challenging projects, many different bridge types. And he'll be talking, one of the speakers talking to you today. The co-speaker is Marian Barth. She's a professional engineer and a project manager, and she works at STV also and has over 25 years of experience. Marian has her BS and CE from Northeastern and her MBA from Babson College. She's also worked on many different types of projects, developing designs for transportation projects and some vertical projects she just told me recently. So please welcome Marian and William.
Thank you, Jeff. Good morning. Let me get started here. Welcome to the Fanny Appleton Bridge, detailing and vibration. I'm going to give you a little project background this morning, some of the steel fabrication and detailing that went into this bridge design, as well as some of the erection details during construction. And then I'm going to hand it over to Bill to talk more in depth about the pedestrian-induced vibration design, as well as our testing that we did once the bridge was constructed. The bridge is located on the Boston side of the Charles River, adjacent to the Longfellow Bridge project, as Jeff mentioned, which you can hear about at 3 o'clock today, if you're interested. And you may wonder, who is Fanny Appleton? Well, Fanny Appleton is the second wife of Henry Wadsworth Longfellow. The bridge is a main thoroughfare for pedestrians as well as bikers between Charles Circle, which is the Red Line T-stop for the MBTA, and the Esplanade. If you're familiar with the annual 4th of July events in Boston, the Boston Pops play on the Esplanade. Hundreds of thousands of people show up, and when the fireworks end, those hundreds of thousands of people are trying to get back to the T to get home. So the live loading on this bridge is literally shoulder-to-shoulder people at the end of every event on the Esplanade. So we did go ahead and up the standard live loading on the design of this bridge. As we said, we worked in a design build contract. We worked for the joint venture, WSC, which included JF White, Skanska, and Consigli. And the fabricator was Newport Construction out of Maine, and the erector was Saugus Construction. We had a very detailed contract in terms of some of the requirements for this particular bridge and some of the aesthetic constraints. And so working with the contractor, we tried to balance the service and strength design along with the pedestrian user experience. So we had a preliminary design that we were given that had an architectural intent for this bridge. The intent was for it to look like a ribbon-like structure, and the arch was supposed to emulate the arches of the Longfellow Bridge nearby. So you can see there's a steel fascia plate that runs along the edge of this entire structure, which gives it that ribbon-like appearance. The bridge also is ADA compliant, is wide enough for shared use between pedestrians and bikers, and we also created an overlook so you can see the Charles River as you're weaving through the trees. Here you can see an overall view of the bridge as it curves in every direction for 750 feet. 100 feet at either end are concrete ramps. 550 are elevated structure. The main span of the bridge is a divergent pipe arch, as you can see here, with HSS spandrel columns, which make up the Verndale truss of the main span. It's 220 feet, and it is supported on either end, as you can see in the foreground, by skewback abutments. And the elevated sections of the approach spans are supported by Y piers. You can see the framing underneath. There's a pair of box girders that run continuously from end to end, floor beams, a cantilever bracket that supports the fascia plate, and the Y piers, which are welded at the top to those girders, have an architectural inset, if you can see on the photo to the right. That was prescribed by the architect as well. In order to create that inset detail, we created these piers as a built-up section at the base, an HSS built-up section, and HSS columns for the arms, and the Y joint was created with a steel casting. Newport Fabrication brought in cast conics to fabricate the casting. We did a design on the casting as well as cast conics as well in order to create this detail and geometry. One of the constraints of the contract was that the bridge was to be jointless. So between the 550 feet from abutment to abutment, there are no expansion joints. So that drove temperature loading to be a very prime design loading condition. And we are also prescribed to have unobtrusive connections, which leads to a lot of discussion as to what unobtrusive really means. However, hopefully you cannot see very well what's in that red circle, that it is unobtrusive, but we did propose to include bolted splice connections on the tub girders to aid in erection. However, we proposed the splice plates are internal to the tub girders and the nuts are on the inside, so they are less visible. And we also had to show along the length of the bridge the location of those splices so that they were less visible to the traveling public. The fascia plate girder that travels the entire length of this bridge is continually curving throughout. In order to create that fascia plate without any kinks or waves, we had some really tight fabrication tolerances, similar to architecturally exposed structural steel. And then those tolerances translated back to the fabrication of the box girders as well. Because the fascia plate is supported by the cantilever brackets off the box girder, those girders had to be matching that same tolerance that the fascia plate had in order to meet fit up. Here you can see the entrance at the ramp. The ramp is 100 feet, it's concrete. You can see that the architecture kind of matches that ribbon type appearance at the top, and then it has a incline down to the foundation. In Boston, right along the Charles, the soil is fairly poor because it's all been filled in. So in order to reduce the amount of substructure and piles for this foundation, for this ramp section, as you can see in the foreground here, we filled the concrete ramp with foam in order to lighten that up. The entire length of the bridge has a epoxy-coated wearing surface on it and a railing system. The infill on the railing system is a stainless steel cable system. And here you can see the overlook that was created looking out into the Charles River. This is looking up to the crown of the arch span. And every piece of steel is curving in every direction throughout the length of the bridge. Here, as you come across the main span, the ramps part of the bridge continues, but we also have stairs as well. So at either end of the main span, there's a set of curved stairs. Here, the curved stairs diverge from the main bridge deck structure. This is a little tricky in creating that fascia plate. It's pretty tight radius on that fascia plate. And also the detailing to merge the two sets of box girders and splice those together created some interesting detailing for the plate connections. You can see here the shear studs on the top of those girders, as well as the stay-in-place forms that were used. The curved stairs span from ground to bridge deck elevation. There's no pier in between. And that's supported by 4 steel girders. The 2 main girders in the middle you see here, being in the shop here. And the exterior fascia plate girder, which we've created into more of a structural member to help support those stairs, and Bill will touch on that more later. Here, just an example of how that fascia plate in curving throughout is very smooth. And here, coming down to the ramp at Charles Circle. The arch sections were delivered in 2 pieces and then spliced together on site. The spandrel columns, the short spandrel columns were welded to the arch section in the shop. However, the longer spandrel columns we could not weld in the shop due to shipping delivery constraints. So we created some alignment studs so that once the spandrel columns get out into the field, they'd be able to set those because, again, they're not perpendicular square. Everything is on a different angle. So those assisted the erector in trying to line everything up. The main deck framing was fabricated in 3 sections for the main span. Here is a picture of the center section getting dropped in on top of the arch, on top of those shorter spandrel columns. So that framing all came out together. And here you can see some of the erection tabs that were used on those spandrel columns to get those in place. They were field welded, field metallized, and then field painted. And the cap plates as well were welded to those tub girders at the top in the field. And with that, I'm going to turn it over to Bill to talk about the pedestrian-induced vibrations.
Thanks, Marian. As you can see, this is a fairly slender arch shape that we have to deal with here. From the very beginning of this project, we realized that pedestrian-induced vibrations could be an issue for this bridge. And generally that occurs when the frequency of a bridge is low enough, it starts to coincide with the actual pace that people walk at. When those 2 frequencies align, you get an increased magnification of the response of the structure. So in some ways you can kind of eliminate that as changing the stiffness, changing the mass, or introducing damping of the structure. By contract, we were required to meet the requirements of the AASHTO pedestrian guide. 1.3 hertz for any horizontal mode, 3 hertz for a vertical mode, or they give an option for meeting an alternate criteria based on the weight of the span. So we met the horizontal. We didn't meet the 3 hertz, but we met the weight requirement. This being kind of a high-profile bridge, we wanted to make sure there wouldn't be any issues that we open this bridge and then have to shut it immediately afterwards due to vibration. So we ended up doing an additional analysis using Cetra. It's a French publication. It's actually referenced by AASHTO. It allows for a time history analysis of the structure, and it takes the accelerations that come out of that time history, and they give you different comfort levels that you can associate those accelerations with. We also used a specialty sub-consultant, RWDI. They ran an independent analysis of the structure, and then later on helped us with the physical testing of the bridge. So just a brief overview of what we did for modeling. It was, a full 3D model of the bridge, steel length, the 550 feet end to end. We had soil springs for foundations, and we put in shell elements to reflect the stiffness of the deck. Our first vertical mode of vibration shown here, it's kind of a vertical and longitudinal movement of the arch. 2.39 hertz, which is less than the 3 that I mentioned earlier. So we knew that we were going to be in this realm of having to do additional analysis. Setra lays out basically 3 acceptable comfort levels for pedestrians, maximum, average, and minimum. If you don't really meet those, then you end up in an unacceptable area. Our initial design landed us in the average towards minimum comfort range. In talking with the owner and MassDOT, we decided that we should probably shoot for a maximum comfort level, which would be up to 5% of gravity. And that's basically practically imperceptible to most people walking across a pedestrian bridge. So the Setra analysis itself is applying a time history load, and that's based on the mode shapes of the structure, the stiffness and mass of the structure, and inherent damping. The chart that you can see towards the right of your screen, at 2.39 hertz, we're kind of on the upper edge of what's susceptible to pedestrian vibrations, and that's reflected in the magnitude of loads that you apply through the Setra analysis. So the dynamic loading that we did apply here, in blue you'll see vertical, the longitudinals in red, and the transverses in green. The transverse loading based on the frequency, Setra doesn't actually require a transverse load for this frequency that we're examining. So we started with that 2.39 hertz, and we were at a minimum comfort level. We decided we had to make some changes to the structure. We looked at about 15 different alternatives. What we really came up with was making changes to the deck system, spandrel columns, and the pier and the pier foundation stiffnesses. For the deck, we had originally started with a normal weight 4,000 psi concrete. We ended up changing out to a 5,000 psi lightweight, foam filled all the stay-in-place forms so we could get rid of any of the additional mass that's not really participating in structural stiffness. The spandrel columns, we went from 7 degree from plumb, which really acted only as a Varendale truss, to a 15 degree offset. I kind of gave it more of a normal truss action, although it still really relies on the Varendale truss action. As Marian mentioned, this is continuous, the structure, so thermal controls a lot of the pier loadings, so we aren't able to stiffen every foundation, but we did go through and examine which piers would allow for a stiffer foundation, and we changed from a 2-pile vertical configuration to a 3-pile battery configuration to add stiffness in each direction. The pier columns themselves, we ended up increasing size, but towards the base of the columns, we also ended up putting internal stiffening. The photo that you can see in the middle of the screen is actually the internal stiffeners running through the base of the column. Those ran through the base plates and were welded on the underside of the base plate to develop forces in them. You can see some of the backer bars are starting to get placed in this section as well. And the stair fascia, the stairs really kind of brace the main span. The original details that we were handed for this, we kind of figured out weren't the best for fabrication, so we found that increasing the size would actually help us for fabrication, but also add stiffness to the structure as well. And you can see some of the internal plates that were required to actually form up the shape, since it's curved vertically and horizontally with an angled plate. So we got up to our design of maximum comfort. Next game, let's physically test this and make sure that it's going to respond the way that we want it to before we actually open this to the public. Again, we didn't want to open it and close it immediately afterwards. It wouldn't be good for us as the designer or the state having that occur. So we ended up getting 48 participants to do our own testing of the bridge, and we placed accelerometers throughout. Initially, accelerometers were placed on the bridge and excited just to determine the actual mode shapes, the frequencies, and what we actually had for damping. The 6 locations that are shown in red up here are the actual locations we did for pedestrian testing. The 2 blues were also used for determining mode shapes. So the first mode that we originally were looking at, we thought was primarily a horizontal mode shape. The actual testing returned that there was a significant vertical component to that due to the torsion of the main span. The other mode shapes by the Setra analysis would no longer be a concern. We also saw a bump in the damping from our testing. So just from our general walking tests that were performed, everything landed within the 5% of acceleration of gravity. That's kind of what we were looking for. We did random testing, and then we did group tests where we had groups of 2 or 4 walk across the bridge. We had metronome set to specifically target the frequencies that we measured during that time. Running Cetra doesn't necessarily require that be examined. It's a short duration excitation to the structure. There's only a short amount of time where that vibration would affect anybody who's on the structure. In our case, this bridge empties into Charles Circle. Really kind of eliminates the possibility from anybody doing any road races or any major events because there's nowhere to put these people after they cross the bridge. Nonetheless, we did do some running tests on the bridge, groups of 5, 10, and 15. The chart here shows what was going on with 10 runners. Again, about 30 seconds is the disturbance of acceleration that's actually observed on the structure, and was still within what we were considering a maximum comfort. So obviously there was a jump between what we did for design and what was done for as-built. So we went back into our original design and adjusted parameters to try to match what was done in the field testing. When we did our field testing, we also didn't have epoxy wearing surface, which would add some additional weight to the structure. So we wanted to be able to match the field results and then make that adjustment and make sure that we still didn't have any issues after that. So the 3 big ones that we probably ran into was we assumed 5 KSI concrete. At 28 days, our average strength was 7.4 KSI. By the time we did testing, we probably had some additional gains beyond that, but a decent change there. Due to the curvature of the bridge, we had assumed that we would take stiffness reduction for cracking. We ended up putting in number 6s at 6, which is very heavy to control the cracking in the bridge deck, and that actually proved to be quite successful. And at the time of cracking, at the time of testing, there was very little cracking on the actual bridge deck. So that initial assumption was conservative. When we developed our design, we also did 2 different foundation stiffnesses, a lower bound and an upper bound. We wanted to use the low bound for our vibration analysis, but we wanted to use the higher for our seismic design to make sure we were capturing what the structure actually might see. And it turned out that the higher bound stiffness was realistically more what we were seeing during the testing of the bridge. From there, there's obviously some differences between what we got in our field measurements and what actually we got from Cetra. Our horizontal accelerations were fairly close to what was determined by Cetra, but we did have differences in the vertical accelerations. We had 48 participants, which I mentioned earlier. When we were grouping people, we did allow for some change of density in that grouping and how tightly people were spaced, but overall, we're not going to meet the same number of people that you would need to fully load the bridge with only 48 people. We were mostly a mix of our design team and construction workers, so our average person was a little heavier than Cetra. And everyone who was participating in this was able-bodied, no children, no elderly people, so actually matching the pace and the frequency of the structure would have been much easier than your average sampling of the public. So for our overall goals, we met the 5% of gravity. That's really what we wanted to meet, was getting a maximum comfort level out of this bridge. And the only case that did not meet that was a case of vandalism where people were intentionally jumping on the structure. Cetra gave us a great way to actually examine the initial structure, to make improvements to it, and then to evaluate it based on a dynamic loading. I think it very well served us in getting the goals for this project. In our final design, I would say we still don't meet the Astro 3 Hertz vertical requirement, but I think going through all this additional analysis and testing, we've shown to the client that we do actually meet the acceleration requirements for maximum comfort. So here's an assessment question, and after that you guys can take down the PDH code if you didn't catch it at the beginning.
the answer.
Do they need the answer now? I don't. Nobody mentioned that. So the answer would be C, acceleration. That's kind of what I've been trying to rehash throughout this. Obviously, everything else in here does play an impact into that.
So we got time for a couple questions. Anybody have any questions?
Yeah, so the question was, we increased the live load from 90 PSF, and doesn't the ASHTO basically cover the situation that we are looking at with the shoulder-to-shoulder loading of this bridge? And for the most part, I would say typically yes. Our contract required us to examine higher loadings up to 150 pounds per square foot. And basically 120 was something that between us and the owners that was agreeable. That 150, once you factor it up, really isn't a possible loading. 90, you could factor it up, and yes, you have that possibility of meeting that factored load. 120 was somewhere in between, where we're pretty sure we'll never actually meet this load condition on the bridge, but is still something you could design into the structure. We have not. I think there are people who would have liked to do that. Based on it being a design build, we have a set budget and limitations to what we can do on that.
You mentioned mode 1 was, you predicted it to be a vertical mode, but in reality it was something else. What was it you said?
So the question was about mode 1 on the vibration. Our initial analysis was primarily that was a lateral transverse movement of the span. When we actually got the accelerometer results, that's when we noticed that there's a larger vertical with the twisting of the main span than was showing up in our initial model.
Vertical acceleration exceeds the limit for comfort. And why use speed mass number? Training to comfort.
So the question was, if we were exceeding vertical, why wouldn't we use tuned mass dampers? Initially, for the contractor, we didn't want to incorporate tuned mass dampers, and equally from the owner's perspective, there's regular maintenance with those. They typically have to be rechecked and tuned every couple years. You have component replacement. So what we ended up doing was the improvements that we made to the structure. Our initial design carried a chunk of budget for tuned mass dampers in case we were going to need them. Basically, we ate that budget up by making physical improvements to the structure to try to make the maximum comfort occur without having to use tuned mass dampers. And that was more a client preference than, for the same cost, it doesn't really matter to us if we installed one versus the other.
The Eurocode has provision for looking at the dynamic effects of pedestrians moving across bridges. Did you look at that at all in your design, or did you compare it to what you actually got in your tests?
Initially, when we started design, we did look at the bridge standard 5400, I think it is. We did a comparison of several of the codes that were out there prior to just using the Cetra for this analysis. Again, that was something that we consulted with the owner on to make sure they were comfortable with using an alternate design code for this kind of project. So the question was the internal splices, were they closed boxes? They are actually a tub shape with a small opening on the top, but from all views they appear to just be boxes.
So you had access?
Yes, we did.
All right, thanks, everybody.
Thank you.
Okay, our next presenters, again, we have two presenters, and they'll be talking about the 41st Street pedestrian bridge, which is in kind of south of downtown Chicago. Our first speaker is DePaul Viamawala. He's vice president and bridge practice leader for the Midwest region of AECOM. He received his master's degree in structural engineering from the University of Wisconsin in Madison. DePaul was the principal in charge for this project, involved from the inception and planning phase all the way through final design and project support. Our next speaker is Singh. He's a bridge lead engineer and associate vice president with AECOM. He received his PhD in structural engineering from Illinois Institute of Technology. He's specialized in highway steel structures and has been a main designer for many large, complicated, innovative, and award-winning highway projects. Please welcome.
Good morning, folks. I see some of the familiar faces also from Chicago, so I feel like it's home. Our talk today is about the 41st Street Pedestrian Bridge. So, sorry, I should hide the PDH code. And I'm going to be joined by my senior bridge engineer, Singh. So the presentation today we have covered in three phases. I will talk about the background. There's a lot of history to this project and just introduction to how we got here. Singh will cover the real part of the structural analysis and design, and then I want to talk about some staging and construction sequences, and if there's time permit, we have a video that we can play, which speaks to the volume of how the job came down. So some of you that is not from Chicago area or do not know Chicago, this is a map showing a bunch of projects that are currently happening in Chicago. A lot of them are from the Chicago DOT and Illinois State DOT. The project that we are covering today is located about 4 miles south of downtown Chicago. It's along the Lakeshore Drive and also span over the active railroad. So it's about 4 miles south of downtown Chicago, right next to the Chicago Bear. So if you're ever coming to that, you probably have driven through that. And a lot of construction happening in Chicago area. So it's a very busy time for us during this year, time of the year. So the project started about 2004. It's almost 15 years, and this was a competition that Mayor Daley announced, and it was only allowed by architects to submit to the applications along with engineers. So there were 6 locations chosen as part of this competition, and the whole point was to create a lake access. Chicago has an ordinance that requires lake access every quarter mile, which is nearly impossible, but city is trying the best they can to create that access points. Part of that came out this 6 locations, and AECOM was fortunate to be part of the 2 of them with our architect Goulet and Clark. So these what you're seeing is exact rendering. The paint that was used, basically brush paint that was used to submit. There were no computer drawings or nothing. So I have a series of renderings that I want to show you, and it was picked overwhelmingly by the public, by the residents on the south side, and we respected that, and we wanted to make sure that we follow through and we deliver exactly what was picked 15 years ago. As you can imagine, as time passes by, it's hard to make those commitments that were done years ago, but we were able to do that with help of City of Chicago. This is just the overall rendering of the site. You see the downtown in the background. So there are 2 locations, as I mentioned, 41st and 43rd. 41st open to the public in December, and 43rd is the lower part of the picture that is currently going to be procurement very, very soon and planned to be in construction late this summer. So it'll be 2 identical projects within quarter mile from each other. Again, just showing you the site. It's a pretty intense site. You have a lake very close to you. So and I'll talk about this later when we talk about construction staging, but it was very unique for us to think through the stuff as to how they're going to bring pieces of steel. Will they barge it? And again, with the procurement rules, we really can't talk to a single fabricator because we have to be fair. So we talked to several fabricators, brought them on the same platform, make sure they understand. And then we also wanted to do the details and plans that are constructible. But as you can just see, and I could not do justice to the site by any photo or any slide, but it is extremely tight corridor. You have lakefront property that has to be protected. There are significant lake users in this area by the bicycles and pedestrian. There are 6 active railroads, and we'll talk about the challenges of those. But these are very, very active railroads, 270 trains a day, and anybody in a freight business would know that that's ridiculous. There are commuter lines and there are freight lines. So there are 4 lines are run by Metra, which is our commuter district, South Electric line, and there are 2 freight lines, CN lines. So pretty intense traffic, and then you got freeway, which we call Lakeshore, which doesn't allow the trucks, but anyway, it has a heavy, significant volume during the rush hours. So we had to work around all those constraints, not only for design, but also for construction side of it. I'm going to walk you through some quick renderings. And again, these are important to see because the final bridge product looks just like that, and we are very proud of the fact that we followed through with the help of city, of course, that we were able to deliver exactly what was promised years ago by an architect. Now, I'm going to say a few things to the architect community. No offense if you're architect, but we love working with them, but they sure know how to make our life miserable. And I don't have a better word, so I'm going to just stick with the word miserable. But what you're seeing here is what we actually improvise, if you will, to the concept. And so the kickers that you're seeing, these are the basket handle kickers. They were not in the plan by the architect. The arch angle was 45 degrees. And so if you just do the 2, and we did that, when the job came back to life after 10 years of planning, we did the model, and you heard about the natural frequency, and I can attest to what you guys went through. And I don't want to put any number to get legal team involved, but the numbers were not right, and the natural frequency was not correct. And we got really concerned, so we did 3D modeling, and we brought in our client to the office and demonstrated that we don't feel comfortable with the 45-degree arch. The deck is curving along with the arch, and absolutely no support. So you can imagine, luckily we are next to St. Louis Arch, but you can imagine how steep it has to be. And if you just do a free body diagram, the center of gravity is way far south. So, the pipe has to be so robust to be able to not only sustain the self-weight, but carry the curving deck and vehicle and the live load on it, and we didn't feel good. So the improvements we made, 3 improvements we made was, and a lot of credit to Singh here, who will be speaking next, is we changed the angle from 45 to 30 degree, or 60, how you measure it. We introduced these basket handle kickers, which, again, beauty is eye of the beholder. I think that looks very well. You'll see a plan view. They look really nice. They go along with the geometry of the bridge. And then there were vertical stiffeners, which were in the deck, which was changed to the hangers. So I think it created a really sleek look to the bridge. And finally, architect came on board, and we were able to work with them. But that's it. I won't badmouth anything. They were great people, but it'd be nice if we were part of the first sketch. Again, a few more renderings of the bridge looking on the Lakeshore Drive. And then this is right next to Active Park. Local community is very attached to it, so we did a lot of renderings to convince them what they are going to be getting. And I'll save the structural part for Singh, but it's the main arch is 2 spans, one over the railroad and one over the Lakeshore Drive, and they both are 240-foot span. They are curving in an S shape, so it's really elegant. This is the cross section. So the main arch is 4-foot diameter. The cables are hung from the main arch, and then it picks up the 2 tubes, which are the deck tubes, which supports the entire deck. So you can just imagine amount of torsion, and you'll hear about it. But the approach also, we were trying to make it very sleek. So the approach on both sides of the main span are 2-span structures. It's a single curving tube, and then followed by the MSE wall. We try to minimize the MSE wall length just so that we don't want to block the lake view from the park. But we had to do economical balance, and we came up with a 2-spans structural and remaining MSE wall. And that's the cross section over the approaches. Again, a single tube, 3-foot diameter tube. One more thing I want to talk about is the temporary bridge. So this was a very unique application. We had a significant discussion with railroads, and there were a bunch of active railroads. Basically, after years of negotiation, they told us that you will have between 1 a.m. and 3 a.m. to construct anything. And rightfully so, because they are carrying a lot of traffic there. And we figured if you were to do that, just to build this bridge, you're looking at years of downtime, flagging cost, and just ridiculous amount of coordination. And any one of you work for railroad, you know it's either their way or the highway. So what we decided to do is let's just not deal with them too much and come up with a temporary bridge. So again, this is not very uncommon. In Chicago area, we do a lot. I know it's been done everywhere. But this temporary bridge, it was very complicated. And it's a very high ticket item too. I won't go in numbers, but it was needed. It paid the premium many times over. We had to make sure that we build this temporary bridge in between the proposed deck and the overhead catenary lines. And there's a next slide which shows you how many catenary lines are there. These tracks are run by overhead power lines. So we had literally 5.5 feet between the proposed bridge deck and the top of the catenary lines to sandwich this temporary bridge. And I don't want to use a cheesy word, but we did 3D model. The red is the temporary bridge. We took upon ourselves to do 3D model. We wanted to be convinced. There are 4 tracks of commuter line and there are 2 tracks of the freight line. There's a space in between, enough to put a shoring tower, but that comes within 25 feet of the clear zone for railroad. So we did 2 designs to make sure that we can either span all 6 tracks for temporary bridge I'm talking about, or we can have a temporary support. We wanted to make sure the contractor had options, and to be honest, we could not get railroad to agree whether would they allow the temporary support or not between the tracks. So we left 2 options on the drawing, on the plans, but both were constructible, and the contractor chose one without the temporary without the temporary middle tower, which was a smart thing to do. But again, we had to literally thread the needle. There was maybe some thin airspace between the temporary bridge flooring and the lines below, overhead power lines below, and the finished bridge deck above. But what it did was give the contractor almost a free slate, complete freedom to do what they have to do over the 6 to 9 months of period, which with a very minimal interruption from the railroad or requirement from the railroad. So again, keep this in mind for jobs like this. Most often they are governed by temporary stuff than the permanent conditions. With that, I will have Singh talk about the structures. Just use the key. There's a clock. Okay.
Okay, this bridge has 6 spans, but today I'm just concentrating on the 2 main spans, as shown on the screen. Around the plan view, you can see the deck is S-curved shape. The arch is only each span is supported by 1 arch on one side of the deck. Also, from the elevation, you can see we have vertical profile. So the pier elevation between the center pier and the end pier is a 7 feet difference. So basically, we have for each arch, there's no symmetry in any direction. So we are dealing with very complicated geometry. Okay, here is some details about main span I just talked about. So the structure, the 2 span, each span is 240 feet. It's inclined 30 degrees from the vertical plane, also rotated about a vertical axis mainly to line up with the deck, because the arch and the deck don't have the same alignment. So this structure basically, all the configuration basically, as Depot talked about before, it's given by the architect. So there's a requirement that we can only use either pipes or box sections, not any other eye or other sections, only pipe or box. So this is a very typical cross-section through the deck. We have 2 deck ribs, 1 arch ribs, so that on the left, the deck rib is 4 feet in diameter. On the right, the 3 feet diameter. Only have support on the left by a hanger. So these will develop a huge torsion, in the deck. This is the end view. You can see there's a kicker to to support the arch. Basically, we are required to maintain the kicker below the deck. So basically what we did, we put the kicker symmetrical to the arch. You know, if you look at the end, up to the joint. Because this is a 3D model we created. Here they're showing one span with CISI bridge software. Basically, all the element in the model, we model all the steel as a frame element, and all the hangers as a cable element. Also, in order to model the construction sequence, we have to assume how those hangers are going to be tightened. At different stage, the hanger will have different forces. So each time when one hanger is tightened, the forces in all other hangers will change. They are very close to each other. So the results, the analysis results show that we have a very large torsion force in the deck. Also, there's a very large lateral force because inclining hanger. So we have a very hard time to design the building and support. Also, another problem we had is low frequency, a natural frequency, so it doesn't meet ASTO requirement. So this is just another view of 3D modeling elevation view. You can see the deck, it's not a level, it's just elevation difference, about 7 feet. So due to all those problems, so we had sub-consultant RWDI model this structure, you know, for vibration issue and also the wind load. Because this is a wing model. So basically, the purpose of this model is to see what's if the structure is going to be stable on the wing load. Also, we need to know, you know, what's the design load, you know, for this special structure. Suppose, do you know how to play this video? Yeah. Oh, okay. Thank you. Yeah, because file size constraint, you know, we doesn't show that good. The next one is this is a vibration model. The purpose of this one basically is we need to know what's the real frequency in the vertical direction and horizontal direction. You know, if this structure is adequate. So the results, we find out that even there's a vibration, but for this particular bridge, the lateral stiffness is quite high. So the frequency in the lateral direction is high. So, but people are more sensitive to the lateral vibration instead of a vertical direction. So the conclusion is that the structure is okay. Shouldn't be a problem. Okay, next I'm going to talk about design, the component design. So here we have many challenges for the structure design. So because all those shapes are not typical shapes, for all those pipe sections, box sections, it's very difficult to put a stiffener inside. So the challenge is how to design those connections. So I will show you those in details. So here it's a typical design formula we took from AASHTO for the arch rib design. Basically, it's a combination of axial force and the bending in the arch rib. So the big thing for the arch design is the unsupported length. So the AASHTO doesn't have much guideline for the unsupported length. So we looked at the Eurocode. So we took this one from Eurocode. Basically, the unsupported length we have two unsupported lengths. One is the in plane. Other one is auto plane. So the buckling mode will be either in plane or auto plane. So from the Eurocode, we got those parameters. The in plane bending buckling mode will be like the one showing on the right. So the unsupported length basically will be the half of the arch length, as shown on the picture. So the in plane unsupported length will be just a span length from support to support. So the deck rib design, because support just on one side, there's a huge torsion. The main force will be torsion. So AASHTO doesn't have any criteria about torsion design. So this one basically is taken from AIC, as shown formula here. Basically, we will consider all those force components, but of course the main contribution for the stress is due to torsion. So we'll consider axial load, bending, shear, and torsion. But shear is a main contributor for the stress. The hanger we used the STM A586 structure strands. It's 2 inch in diameter, as shown in the picture. So this is a typical transverse Goulet design. It's as shown in it's a box section. So it's welded to the deck ribs. Yeah, because I'm running out of time, so I'm not going to take too much details. So for the connection design, basically the AASHTO doesn't have much guidelines. So we took an international code called CIDECT. They developed a formula it's based on testing. They have a lot of testing conducted in Europe and Japan. So we use this formula for the connection design. Next one, I'm showing the end transverse girder design. This is, I would say, the most complicated structure detail here, because this girder here, we have to design for a large torsion force. So we need a hold-on device. So on the left, you will see there are 2 hold-on devices because large uplift force. On the right, we also have a very large lateral force. So the bearing on the right has to take a very large lateral force. That force is about 70% of vertical force. So this is a special bearing. But for redundancy, for the safety, we also added a jacking device in the middle. It's a permanent jacking device for maintenance, actually also for initial construction, also for future maintenance. So there's a vertical cantilever beam to prevent the girder to move to the left. So in the normal operation, so there's there's a half-inch gap between the beam and the bracket. So in the case of the failure building, so the bracket will hit the vertical column. Also below the bracket, you see there's a space. So jack can be placed over there to be jacked for the building maintenance and installation. Okay, this is just a typical section and beam. So this is the anchor, actual picture showing the holding device. So this is actual building. This is a center girder. So I'm not going to talk too much about this one, running out of time. So this is the hanger. The hanger is just a single plate. There are no internal stiffened plates. So the hanger will act as like a stiffened plate. So this connection at the deck, this is the only place we have internal stiffeners because large concentrated force. So this is a real picture taken during construction. Okay, those are showing the pier elevation. This is the actual the pier as built. So this is a base, arch base. Paul?
Sorry. Thank you. Okay, so in essence of time, I want to play the video if I have a minute, but I want to skim through some slides about staging and construction. And the real point I want to make is we put together a plan set, and of course by talking to a lot of contractors and suppliers on a level platform, and make sure that what we put out is constructible, biddable, including how you ship the material and what have you. So we went through a series of erection sequence, and I'm going to skim through this, but we are very fortunate or privileged that the contractor pretty much used that sequence, so it kind of took a lot of guessing game in the field. But we sorted through how they will build the temporary shoring towers, how they'll build temporary bridge, how they will erect the arch, and with some modifications they pretty much use that scheme. So it saved a lot of time on the owner side and also on the contractors and RFIs and what have you. So it always pays off to think through how some similar jobs going to come through. I want to give some attention to Bentech. This is a steel conference, and Bentech's been I don't know if they're in the room, but they were a great supporter of this project. Some real nice images they shared with us for the main arch pipe and the deck ribs, and they were extremely good folks to work with, very knowledgeable. We call them many times to pick their brain during design. So we make sure that we put something together that's constructible. Again, the slides show how the whole job came together. I'm going to try to skip through that, but basically, the approaches were built first. This is the meat of it, the temporary bridge, and you can see the train approaching. There has never been, another view, there has never been a shortage of trains under the temporary bridge, and it allowed the contractor to pretty much work at their own pace. This is my favorite shot. This is where the steel, the main ribs arrived. It went through hundreds of permits and traffic jam and a lot of show. So some people followed it. I was getting texts at 10:30 at night that it's around here. I'm like, this is cool. So anyway, these are some good erection sequence, how the stuff came together. One thing we had was we thought they would build the railroad span first and then the lakeshore drive span second, but I think the contractor altered that. They built the lakeshore drive span first and the railroad span second, and I think it was pretty smart because they got all the kinks worked out in the roadway span, and this way the railroad span just came together very nicely. So they wanted to minimize any unknowns, any challenges for the railroad area. So it was pretty smart by the contractor to do that. Again, some sequence of deck forming, and then final deck pour and final finished product. There was this is the complete bridge. We are very proud of it. It looks pretty nice with the Chicago backdrop. This is half of them are from Washington, D.C., Federal Highway. They all came together. This was a Tiger Grant, so it was extra special because a lot of entities were involved, and it was very well received by public. We have notes by public, and they have love notes on the bridge, and it's pretty unique for an engineer to be part of that. So there's one question. I try to make it simple. It's a first session in the morning. So what is the diameter of the main arch rib C? I guess I'm just trying to be easy. So his answer is C, 4 feet. And there is a PDH code, 83221. If there is a minute, I can play the video? Yep. Okay, if it works.
I have one quick question. Looks like we got one here. Go ahead.
Oh, sorry. Sure. Can I play the video? Is it okay if I can play the video for a second? Okay. Is there a volume? There's a volume. I don't know how to control that, but.
Like it's working.
Oh. It's interesting. The whole screen went blank.
Yeah. Well, it looks cool up here.
Yeah. Sorry, folks. It's playing here, but
Yeah.
I don't know why it's not playing there.
Sometimes there's a lag or something. But, yeah. Well, if we can give all our presenters one last hand, and thanks for coming to session B2.